Okay, good morning and happy Monday to everyone. Today we're going to talk about the Laplace transform, and it's such a nice topic with so many new and fresh ideas that I'm really envious of those who will see it for the first time, which I hope is everybody. But before I get to this, does anybody want to ask any questions regarding previous material or the upcoming exam? I remind you that our exam is on Friday. I have already given a very detailed description of what the exam is going to look like. If you look at the recordings, you will see where that is. It's like the 10 last minutes of that particular lecture.
Yes,
And
if you will ask a question about Cauchy Euler equation, you will ask us to such as use this method or just we should to figure this with ourselves about Cauchy Euler.
yeah, no, I understand, and this goes to everyone. I don't think I will try to specify what method needs to be used. I will ask the question to solve an initial value problem or a general, or find the general solution of some differential equation, and I will leave it up to you to figure out whether it's Cauchy-Euler, whether it's exact, or so. No, I'm not going to specify what method needs to be used. Okay, it's part of your task, of your it's part of the challenge to be able to distinguish between the different types of equations. Okay,
Thank you. Thank you.
but I'm going to give you the questions in the order that appear in the study guide. So it's not going to be that hard to figure out, at least what is going on. And of course, so far we have seen just first order and second order equations. And if you get a first order equation, it has to be either separable, linear, or exact, right? If it's a second order, I think you will have to see, does it have constant coefficients? Is it homogeneous? Is it non-homogeneous? And those questions are going to help you sort out what needs to be done quite easily, I think. I hope. Okay. Any more questions, please? Okay. So before introducing the Laplace transform, I would like to discuss a little with you what the idea behind this whole business is, because it's really a wonderful idea. And one of the things that I hope has been conveyed so far is that there's really no bound, no restriction, no limit to how far we are ready to go, we're prepared to go, we're willing to go in order to solve differential equations. And whether that is algebra, whether that is integration, whether that is even a numerical method like Euler's method that can be actually greatly improved. The version that we did was the one which is like 300 years old, and there are many improvements to Euler's method. So the bottom line is that the methods that are to be used in this context have no restrictions. You can do whatever you like. And it is true that once you go over to partial differential equations, there is such a fundamental need to even know that some equations do have solutions that pretty much anything goes. So what's this new idea? What is hidden behind what we're going to talk about today, which is something that I feel is completely new from both an analytical point of view and a conceptual point of view. So let's start with the conceptual part. Okay, so at first, it will seem a quite, our whole treatment of the Laplace transform will have some ups and downs regarding the impression that we should have regarding. So what I mean by that, at first the idea seems amazing. So you start with an equation, right? So you start with a differential equation. Let's say some very simple differential equation for the moment being. Let's say an equation with constant coefficients, let's say. And what you do is you consider this equation in the space of functions of t, of the real variable t. And what happens next is you find a way to translate that equation into a new space of functions of a complex variable S, so that this equation becomes an algebraic equation. So in other words, it doesn't have derivatives anymore. In other words, what you build is really a dictionary between two different worlds. The one world consists of functions of t, the usual functions that we have been talking about. Of course, instead of t, you could choose your own favorite letter variable, but allow me to use t in this chapter. Again, that should not be considered any kind of limitation. And the same, of course, goes for the letter variable that we use in this other world, in this, if you like, parallel universe, where things behave differently, but pretty much the philosophy that we're working on is that every object in this world has its counterpart in this world and vice versa. And this philosophy is justified once it's laid out in a careful way. That is, one cannot be careless at this point and just assume that anything on the one side can be translated to something on the other side, because that's simply not correct. However, once you impose the right conditions, that's absolutely true. And like I said, what is important for us is that this transition takes us from a differential equation to an algebraic equation. And of course, if somebody asked us to choose between having to solve a differential equation and having to solve an algebraic equation, when I say algebraic equation, I mean a regular equation that doesn't have derivatives. It just has an unknown function and algebraic manipulations, then we should always go with the algebraic one, right? I mean, you can just use high school algebra and solve that equation and find your function. So the idea here is that we take our equation, we translate it into a presumably simpler equation in a completely different space, we solve it, and then of course we have to find our way back, because once we solve it, we find an object in this world, and somehow we have to find out what it corresponds to in our original universe. Okay, so we have this kind of transition, and there's another thing here that is important to understand. Where does all this come from? I mean, have we seen anything like this so far in our mathematical experience, where you start with a function and you produce a different function. And when I say different function, a function that seems structurally different. So of course, you've seen processes in mathematics where you start with a function, you find another function, you find the derivative of a function, right? You find the integral of a function. But that's not what we're going to talk about here. I mean, if I were to put those functions side by side that we get, and in some sense, not tell you the story that I'm telling you here, you would have absolutely no way of knowing that there is a relation between those functions. Whereas if I put the function and its derivative next to each other, most of you will guess that here's a function and here's its derivative. So nothing so incredibly strange. So the natural question that we should be asking here is, where did this all come from? Okay, how do you wake up one nice morning and start associating with a given function some other function defined on some different set of inputs? And here is where we have to understand that this was a process that was that originated in the 18th century and solidified in the 19th century. And actually, I should say mostly 19th century. And then, of course, it took off in the 20th century. And we should say a few things about how it all started. So the idea was pretty much to, you might argue that one possible path to our story is through Fourier analysis. And we're lucky enough to be able to see some Fourier analysis later in this course. And pretty much the idea behind Fourier analysis is you start with a function and you would like to represent it. That's why I put this tilde here. I don't want to put equality sign yet. As an infinite series consisting of sines and cosines. Such an attempt is analogous to representing a function as an infinite polynomial, as a power series. Well, instead of going after polynomials, we go after what we consider equally simple functions, which are sines and cosines. So it turns out that when you try to compute these coefficients, you get expressions that look like this. You get something like f of t, a cosine of nt dt, something like this, over an appropriately chosen interval. I don't know, something like negative pi over pi, and you get some factors in the beginning. The point is that you get such an integral. And in this integral, you can see that you're inputting a function, and there's this parameter n that eventually forces the whole thing to depend on n. So you know that by computing this expression, you will find something that depends on n. So all of a sudden you have a novel concept, if you will, according to which you have an integral that has two letter variables in it. The integration one, the one that corresponds to integration, and another one that corresponds to some other parameter that is there for a reason. This happened in the case of Fourier analysis. So when people observed that in the 19th century, they realized that they could start a process that could produce these Fourier coefficients that, as I promised you, we're going to start later. But then they realized that a new whole possibility was presenting itself in the sense of creating an integral that had the usual variable and that new parameter, and then eventually getting something that would depend upon that new parameter. So that was the ideal. So the idea is take your function and integrate it against something that depends on more than one variables. The variable of integration is going to be absorbed by the integral, and then the other variable is going to emerge as the parameter of the new function. And it's fair to say that this philosophy gave rise to a whole host of such constructions. So people got all sorts of such transforms that played different reasons. And of course, like I told you, this whole theory completely took off in the 20th century, where people looked at very, very general such constructions and came up with very, very interesting such relations. So with this introduction as to how this process took place, now I can give you the, you will see it. I mean, when I say absorbed by the integral, I mean that t, once you compute this integral, the answer is not going to contain any t, because t has been consumed by the integration. That's what I mean. Okay, and here comes your Laplace transform. So we begin, so let f of t be a function on 0 infinity. And you will see, as I told you before, one has to impose some conditions on this function. So let f be such a function. And we define the Laplace transform of f to be denoted by uppercase f of s, which will be the integral from 0 to infinity of e to the negative st f of t dt. This is the Laplace transform. Okay, and now you can see what is going on. You can see that you have this quantity that depends on s and t. T is the variable of integration. It is, I said, absorbed before, I said consumed. You can put any descriptive verb that you like in that case. And eventually you get something that depends simply upon s. You get something that depends upon s. And this is the Laplace transform. Now, the conditions that f satisfies, so f here should be of what we call exponential type. And piecewise continuous. What do I mean by these two? This is where sometimes I prefer to say under reasonable conditions. And the reason behind choosing to say under reasonable conditions is that these conditions are usually met for all functions that we see here. So exponential type, we really mean that it doesn't rise too much. So it's less than k times e to the ct for k comma c, let's say greater than 0 for some, and t large enough. And when I say piecewise continuous, I really mean you have a function that does not have to be continuous at every point, but then again, it has just jump discontinuities at a sparse set of points. So you will see that at some point we will want to work with such functions. It seems that at first somebody might protest and say, well, have we ever seen functions in any of our courses that are discontinuous? And the truth is that in this instance, we're going to have to work with functions that can possibly be discontinuous. So yes, I mean, the answer is that yes, it may happen here. Any questions before I start giving you the first few examples of Laplace transforms? Okay, so let's compute something. So let's compute for the constant function one. So first of all, no, actually, before I give you this, let me actually give you an alternative notation. So the Laplace transform of f of t will also be denoted by L f of t, like so. Okay, so we will denote it like this, and we will think of this as a function of s. So this calligraphical, right, for Laplace. And you have these curly brackets, and you have your function t inside. And my first task is to identify the fact that the Laplace transform is a linear map, as we say. So if you feed it the sum of two functions, it will spit out the sum of the Laplace transforms. So differentiation and integration do have these properties, as we should all remember. And also, if you feed the scalar multiple of a function, you will get back the same multiple of the corresponding Laplace transform. So these two properties tell you that Laplace transform is linear. Okay. Let's do a computation. So let's find the Laplace transform of the function one, of the constant function one. Don't assume that the Laplace transform of a constant function should necessarily be constant, or it should look like this, or anything else of that type. Let's just compute it, right? So what is it going to be? All you need to do is integrate from 0 to infinity of e to the negative st times 1 dt, right? And you really have the to find the antiderivative of e to the negative st, and that is going to be e to the negative st over negative s from 0 to infinity. And of course, when I say infinity, what I mean is the limit of this quantity as t tends to infinity, which is 0. Because here we're supposing that s is positive, or if we take into consideration what I told you before, that we're talking about positive, about complex numbers, the real part is positive. So this is really 0 minus e to the negative s, e to the negative 0 over negative s, which is 1 over s. So here's our first computation for today. The Laplace transform of the function 1 is 1 over s. Okay. Here, let me bring to your attention, I know you will have to follow what I'm saying, because I know that my s looks awfully like a 5 And some of you might look at this thing and if you're not following what I'm saying, might think, oh, 1/5. Why 5 and not 7? No, it's 1/s. So sometimes I will be putting the, what are they called? The serifs, in order to emphasize the fact that I'm not talking about 5, I'm talking about s. Okay. Now, how do we compute? In general, it would be a good idea to compute the Laplace transform of t to the n, because then we would know how to compute the Laplace transform of any polynomial. Remember, we said it's linear, right? So we would have to just compute the Laplace transforms of the monomials and then apply the appropriate coefficients. So so we have from 0 to infinity of t to the n e to the negative st. And what do you do here? You will have to do integration by parts. So to have integration by parts, you need to acknowledge something as a derivative. And this is the derivative of e to the negative st over negative s derivative, which is going to give you t to the n e to the negative st over s from 0 to infinity minus the integral of n times t to the n minus 1 e to the negative st over negative s dt. And interestingly enough, this thing, if n is greater than or equal to 1, and we can suppose that it's greater than or equal to 1 because we found it for 0, will actually give you 0, because when you plug in t equals 0, that will give you 0. And when you take the limit as t tends to infinity, this thing decays very fast and gives you 0, which means that the only thing that makes it out of here is this part right here. And this part is going to give you pretty much, so this is going to be 1/s times the integral from 0 to infinity. Actually, there is an n here, of t to the n minus 1 e to the negative st dt. So you will find this, which means that with each power, you gain a factor like this. So for example, let's say that you want L of t. So L of t will be, actually, let me identify the general formula that I got. So I got that L of t to the n is the same thing as n over s times the Laplace transform of t to the n minus 1. And, as I'm doing all these algebraic manipulations, my feeling is that some of you feel already quite overwhelmed and look at this thing and say, what in the world is this? I haven't seen anything like that before. And that's precisely right. You've never seen anything like that before. And this particular chapter is going to be technical, and it's going to require a lot of repetitive work where you will need to write these things down, rewrite them, erase them, write them again, try to remember these formulas till eventually you master them. And let me go back here and compute, for example, a few of these till a formula emerges. So you will see that L of t, according to the formula that I just gave you, is going to be 1/s times L of 1. But we said that L of 1 is 1/s, so this will be 1/s squared. So L of t is 1/s squared. Let's find L of t squared. What is L of t squared? According to this formula, it's going to be 2/s times L of t. And L of t is 1/s squared, so this is going to be 2/s cubed, right? Could you please go ahead and compute for me L of t cubed, L of t to the 4th, L of t to the 5th? Let's see if some formula emerges here. Can you please compute this? Again, you will be using the formula L of t to the n is n over s times L of t to the n minus 1. And of course, you know that L, as we just said, L of t squared is 2 over s cubed, right? We said this. You're quick, huh? Okay. Yeah, that's right. Okay. That's right. Your classmate just gave the answers. I would like to give you 1 minute to work out a couple of them, and then we'll see them together. Okay, let's see them together now. So we have L of t cubed is going to be 3 over s times L of t squared, which is 6 over s to the fourth. L of t to the fourth is going to be 4 over s times L of t cubed, which is going to be 24 s to the fifth. Oh boy, this is a nightmare. S to the fifth, right? S to the fifth. Okay. And L of t to the fifth is going to be 5 over s times L of t to the fourth, which will be 120 over s to the sixth. So can anybody tell me, after all of this, does anybody have any conjecture, any guess for what L of t to the n should be? What's the correct interpretation for L of t to the n? Any guesses? Do you recognize these numbers? 6, 24, 120. Very good, excellent. Good work. N factorial over s to the n plus 1. So that's our first formula. Okay. So please use this formula and the linearity to tell me what is the Laplace transform of 3t squared minus 7t plus 5. Okay, please find the Laplace transform of this. Okay, so I hope you all found the right thing, which is, so you need to just find the Laplace transforms of t squared, t, and the function 1, and multiply them by the corresponding coefficients in front. So this will be 6 over s cubed minus 7 over s squared plus 5 over s. Do you all agree? And these are s's here. Let me put the serifs. Okay. Any questions, please? You know what? We're going to also play the inverse game very soon. So we might as well start playing it right away. So step by step. So can I ask you, if I give you this 7 over s to the fourth, can you figure out what was the function whose Laplace transform was 7 times s to the fourth? Can you figure out how much it should be? Okay. If you were to guess, so I tell you that the Laplace transform of a function that I'm hiding from you is 7 over s to the fourth. And the question is, what is the function? What is the function? No, not really. You have to be careful there. You have to be careful. Yep, that's right. That's right. Let's see why. Let's see why. The thing is, you want to create n factorial over s to the n plus 1. So since you have s to the fourth, what factorial do you need? You need 3 factorial. So you have to rewrite this as 7 over 6 times 6 over s to the fourth. So I multiply and divide by 6. I want to create this 6 over s to the fourth because it looks like it follows the pattern n factorial over s to the n plus 1. So now I know that this thing comes from t to the third. So the answer is 7, 6 over t to the third. Let's do one more. Let's do one more. How about L to the negative 1 of 10 over s to the fifth? Okay, give this a try. So what is the inverse Laplace transform of 10 over s to the fifth? Remember, we said we want to have a dictionary. We want to be able, at first, we want to be able to compute the Laplace transform. And then we also want to be able to go back. So if somebody gives us a Laplace transform, we want to know what it came from. So now you need a 4 factorial, which is 24, right? So you need to create a 24. So multiply and divide by 24. And this is the same thing as 5 over 12 times 24 over s to the fifth. And of course, this is the Laplace transform of t to the fourth, right? So this is 5/12 t to the fourth. Okay, that's it. Okay. Questions? Why don't we take a break? Why don't we take a break? Okay, welcome back. And are there any questions from what we did before? So I would like to give us more Laplace transforms. And let me clarify something here, because I would like to make this quite clear for everyone. that you see how in order to compute Laplace transforms and give you examples, I had to compute integrals, right? Basically, I'm going to do these integral computations for you, which means that from now on, you will be using the ready-to-go formulas that I'm giving you. So the first ready-to-go formula, of course, for today was this one. So every time you will never have to compute an integral yourselves. Okay, my apologies to those that were expecting that you will have cool integrals with two parameters, but basically you will be using these formulas right away, directly. They will be given to you. Okay. So now I would like to compute two other Laplace transforms. So I would like to compute the Laplace transform of, where am I? Let's go here. The Laplace transform of cosine t, but let's make it a little more general, cosine of bt, and the Laplace transform of sine of bt. I would like to compute these two. And guess what? This is going to be a little surprising, and I hope amusing. I'm going to compute these two Laplace transforms simultaneously. Simultaneously. Does anybody guess how? What I'm going to do in order to compute these two Laplace transforms simultaneously? What am I going to use? Any guesses? No. I've never used tabular integration in my life, right? So I don't think I'll start today. There's something else that we said regarding cosines and sines this semester that was really, really cool, and you saw it for the first time. Euler's formula. Great job, Zoe. Euler's formula. That's what I'm going to use. So I know that e to the ibt is the same thing as cosine of bt plus I sine of bt. So I'm going to try to compute the Laplace transform of this. And when I find the Laplace transform of this, I'm going to break it into real part and imaginary part, and the rest will be easy. So I have the Laplace transform of e to the ibt is going to be the integral from 0 to infinity of e to the negative st e to the ibt. And now I do this little trick. I write this as the integral from 0 to infinity of course, somebody would say here, why do you do this? Why don't you give us the formula right away? I could do that. I could have given you the formula right away. But I love integration, right? Integration is so cool. So this will be the same as e to the negative s plus ib e to the negative s plus ibt from 0 to infinity. As usual, the limit as t tends to infinity is going to be 0. And pretty much all you get is what you get if you plug in 0, which is 1 over negative s plus ib. To make this work, you will need to multiply and divide by the actually there should be an extra negative sign, so that should be s minus ib, because the 0 part is being subtracted. And now what you do is you multiply and divide by the conjugate quantity, and this will be s plus ib over s squared plus b squared. And you can break it into real part and imaginary part, plus I times b over s squared plus b squared. And that's it. That's it. So this will have Laplace transform, which is the real part, and this we'll have Laplace transform, which is the imaginary part. Okay, so here are our formulas, our two new formulas. The Laplace transform of cosine of pt is s over s squared plus b squared, and the Laplace transform of sine of pt is b over s squared plus b squared. Okay, so what is your job now? Your job is, you will never have to, I mean, you need to know these formulas, but you will have to apply them in a specific context. So for example, can you please tell me what is the Laplace transform of cosine of 3t, and what is the Laplace transform of sine of 5t? Could you please use the formulas on the top and tell me what these two Laplace transforms are going to be? Very nice. Yeah, that's right. So this will be s over s squared plus 9. And the second one? So s, let me put this serifs. Okay. And the next one? Very nice, very nice. 5. So this is 5 now on the top. S squared plus 25. Very nice. Very nice. And now, how about we play the opposite game? What if I told you what is the inverse Laplace transform? So what would give you 2 over s squared plus 7? Ouch. And what would give you 3s over s squared plus 1? Can you please give me this two? What function would have had, so the inverse question, we're playing Jeopardy here. The answer is 2 over s squared plus 7. What is the question, right? What is it going to be? So here you can see that the numerator is constant, right? Please notice that. So since the numerator is constant, can you tell me, yeah, that's cool. It looks correct to me. Can you tell me what do you expect to have involved in this answer? Do you expect sine or cosine? Sine, very good. So once you realize that you expect sine, you need to create this pattern right here. So you have this 7. 7 has to be the square. So 7 is the square of what? And the answer is of square root of 7. So you need to rewrite this as s squared plus square root of 7 squared, right? And then you need the square root of 7 on the top, which means if you need the square root of 7 here, you should multiply and divide by. So that will be 2 over square root of 7. And now the answer is going to be 2 over square root of 7 times sine of square root of 70. This one is much simpler because it's s over s squared plus 1. The 3 is just redundant. This will be 3 cosine t. It's much simpler. Okay. And that's it. Okay. Questions, please. Okay, let's look at some other Laplace transforms. So what is the Laplace transform of the exponential function, e to the at? Again, I could give you the answer, but let's do it. What I'm doing now is something that you will not need to do yourselves, right? We already clarified this. So the trick is to rewrite this as e to the negative s minus a times t, right? I mean, you have the same base e, so you add the exponents. And this will be negative 1 over s minus a e to the negative s minus a t from 0 to infinity. Again, the limit as t tends to infinity is 0, so this will be 1 over s minus a. So here's your other formula. L of e to the at is 1 over s minus a. Okay, so if somebody asks you what is the Laplace transform of e to the 7t, then the answer is 1 over s minus 7. Okay. Questions? So here comes a really cool one now. Here comes a really cool one. In general, if somebody gives you the Laplace transform of any function like multiplied by f of t, okay, then what you will get is the Laplace transform of little f, but instead of computed at s, computed at s minus a, where f of s is the Laplace transform of f of t. What do I mean by this? So let's compute the Laplace transform of e to the 3t times t squared. Okay, so normally the Laplace transform of t squared is what? 2 over s cubed, right? But you're supposed, instead of s, to put s minus 3. So 2 times s minus 3 cubed. Okay. Let's do a few more of this. Let's do it. Let's get used to this. So the Laplace transform of e to the negative t to the third. How much is this? And then the Laplace transform of e to the 2t cosine of 5t. And then the Laplace transform of e to the 3t sine of 60. Okay. Look at the formulas that we just gave and try to give these Laplace transforms, please. Okay, let's see them together. So the first one is going to be 3 factorial, which is 6 over s plus 1 squared, s plus 1 to the 4th, I'm sorry. Why s plus 1? Why s plus 1? Can anybody explain to us why s plus 1? Exactly, because it's minus negative 1. Excellent, excellent. The second one is going to be s minus 2 over s minus 2 squared plus 25, right? So you do it as if you had just cosine of 5t, and you replace s by s minus 2. And the last one is going to be 6 over s minus 3 squared plus 36. And that's it. Okay? Okay. Going the other way around here can be a little trickier, but I do have a homework problem for you, and that's why I wanted to discuss it a little. So I would like to do something similar to the third. Oh, there's something else which is really cool that I would like to show you. How about we do this? T squared times 5 to the t. This is really cool. T squared times 5 to the t. Can you do this, please? Can you give this a try? Okay, the question is, how is it related to what we just did? I mean, I see 5 to the t. I don't see e to the 80. So can anybody help me here? What am I going to do? What is 5 to the t? Ah, very nice. 5 to the t is the same thing as e to the ln of 5 times t. Okay, so this will be s minus ln of 5 to the 3rd power. And on the top, we put 2 factorial, which is 2. And that's it. Yeah, this is really cool. Okay, and I love asking things like this on the exam. Okay, I can't contain myself. Okay, yeah, this is a hint. This is a hint. Now, I would like to do something very similar to what is in the. So let's say that you have something like this: the inverse Laplace transform of s over s plus 3 square plus 7. Okay, give this a try. I have an almost identical problem for you. Could you please give this a try? What do you think we should do here? what is the first thing that we should worry about here? Can anybody tell me? Yeah, it takes a little more work. It's not just that. Because the problem is, do you see how there's an imbalance here? You have s plus 3, but then you have s. That's a problem. That's a problem. So what do you do here? The idea goes as follows. So you need to create that s plus 3. You need to have, so you need to rewrite this as s plus 3 minus 3 over s plus 3 to the second plus 7. So now you break it into two pieces. And write this as minus 3 over s plus 3 plus square root of 7 squared. And now this is ready to go, right? Because you have your square. It looks like this. It looks like s minus a over s minus a squared plus b squared. So you know that this comes from e to the at cosine of bt. You know that. So that's ready to go. But this is not ready to go because what is bothering you here? Can anybody tell me what is bothering you here? What is the thing that should be not that way here? Right, not 7 though, not 7. It should be not 7, square root of 7. No, it should be square root of 7. It should match what you have in the parentheses. So you will rewrite this as L to the negative 1 of s plus 3 over s plus 3 squared plus square root of 7 squared minus 3 over square root of 7 square root of 7 over s plus 3 squared plus square root of 7 squared. Now we're ready to go. And the answer will be cosine of, or I should put the e to the negative 3t cosine of square root of 7t minus 3 over square root of 7 times e to the negative 3t sine of square root of 7t. Okay. There you go. This is really cool. Okay. I think you have more than enough to deal with the homework for next time. And now all the material for the exam is completed. There is no the other way around. Let's see. Why would it be the other way around? Right. Can you be a little more specific? My apologies. I mean, the easiest way to see whether we're doing the right thing or not is multiply this back and see that this will cancel that. Okay, and so it's the right thing. Okay. Square root of 7 cancels square root of 7, so you get 3 on the top. So that's the correct thing. Okay. So anyway, as I was saying, there's no discussion tomorrow. Of course, there is one on Thursday that I think everybody should attend, regardless of whether you register for Tuesday or Thursday. I mean, since there is no discussion tomorrow, everybody please go on Thursday session. And as I told you before, please go to that session anyway. Okay, go to both sessions anyway. Okay, that's my advice. I haven't taken the attendance today yet. Okay, so for our attendance, could you please send me the answer to what cosine of pi is? Okay, write down what cosine of pi is. Don't write cosine of pi, write what number it is. Okay, and that is our attendance for today. And does anybody have any questions, please? Does anybody have any questions? Yes, I want you to learn these things. Yeah, I want you to learn these things. Okay, yeah, you should know your formulas. I think we clarified this in the beginning, right? I mean, you should be on my case if I allowed you a formula sheet, because it would be as if I'm saying that you cannot remember these things. So remember, I have office hours today at 11:50. So please stop by for whatever questions, and I'll be happy to answer that question also on Wednesday. Okay, but maybe it would be best if you came to my office hours. So everybody be well, study for your exam. As we said, no notes, no cheat sheets or anything of that type. Just you and your knowledge, what you have learned. Okay. Anybody who ever tells you that learning this stuff takes anything other than a lot of work, you may want to question them to see if that's what is right. Anyhow, be well. I'll see you on Wednesday.